So the last type of asymptote of a rational function that we need to explore are slant asymptotes or oblique asymptotes. And we say that a rational function has a slant or oblique asymptote when the degree in the numerator is exactly 1 degree greater than the degree of the denominator. So in order to find the equation of a slant asymptote, we need to use long division with polynomials. So with long division with polynomials, we're going to be dividing the numerator of the rational function by the denominator of that rational function. And this simplification is going to produce a linear equation, a slanted graph, plus a simplified rational equation. So this linear equation, or the quotient of the division, is going to be the slant. So our slant asymptote is going to have the form of the quotient, which again is a linear equation. So this is going to have the form of y equals mx plus b, where m and b are real numbers. Now, I know that long division with polynomials can sound a little bit scary, so to help make this less intimidating, let's go ahead now and consider the following example. So to help us better understand slant asymptotes, let's go ahead and find the slant asymptote for the rational function f of x is equal to x cubed plus 5x squared minus 4x plus 1, all divided by x squared minus 5. Now, we know in order to find the slant asymptote, we want to divide our numerator by the denominator. And notice the polynomial in the numerator is in perfect descending order. We have x cubed, x squared, x, and then the constant term. However, in the denominator, we have x squared minus 5. So to help us prevent any algebra errors, I'm going to rewrite the denominator as x squared plus 0 times x minus 5. So let's go ahead and set this long division up. So when we're looking at this and getting ready to do this division, we want to be thinking about the first term, x squared, and you want to be looking at the first term underneath. And you want to ask yourself, x squared times what is going to produce x cubed? So when thinking about this, if we break up x cubed into x squared times x, we can see that the missing term we need is x. So we have x times x squared, which produces x cubed, x times 0x, which gives us plus 0x squared, and last but not least, we have x times negative 5, which gives us a minus 5x. Now I want to pause for a cause here. Notice if we left this as it is, we would have x cubed plus x cubed, which would give us 2x cubed. But we want these terms to cancel. So don't forget that this is still long division that we know from algebra. So we are subtracting these terms. So keeping this in mind, this negative is going to change the sign of each of these terms within the parentheses. So now that we've distributed the negative, we can see x cubed minus x cubed will cancel to 0x cubed, or just 0. Then we have 5x squared plus 0x squared, which leaves us with 5x squared. And then we have negative 4x plus 5x, which leaves us with x. So this is a great checking point. You always want that first term to be 0. It's a great way to check our sign. Now, coming back, again, we think, all right, x squared times what is going to give us 5x squared? So again, if we break that 5x squared up into 2 pieces, we can see that x squared times 5, where 5 is that missing part. So don't forget here, we also want to bring that next term down in our sequence. So then last but not least, we have 5 times negative 5 is minus 25. And again, here, if we left this as it is, those 5x squared plus 5x squared is going to give us 10x squared. So we want to make sure that we subtract to change the signs. So now we have 5x squared minus 5x squared for 0, plus x, and then plus 26. So notice x squared doesn't go into x, so this is the remainder. So now that we have the remainder, we can go ahead and rewrite this rational function as the sum of the linear portion plus a rational portion. So from this long division, we are able to rewrite our given rational function as this linear equation, x plus 5 plus the remainder, x plus 26, over the divisor, x squared minus 5. And this linear portion here is our slant asymptote. So using this long division with polynomials, we were able to break down or decompose our rational function into the sum of a linear and rational function, which allows us to identify that we have this function has a slant asymptote at the diagonal line, y is equal to x plus 5.